You have a quiz that is due today at 2 p.m. You have a quiz that goes up today at 12 p.m. and that will be due at 2 p.m. tomorrow. And today, what we're going to do is we're going to continue our conversation or our discussion of gases. So yesterday, what we talked about were a couple of different laws related to gases. And um, we talked about Boyle's law. We talked about, Boyle's law, which is our relationship between pressure and volume. We then discussed, sorry about this, everyone. Share, share, share. There we go. We talked about Boyle's law, which is the relationship between pressure and volume. And if you remember, pressure and volume are related in this way: P1 V1 equals P2 V2. So this is Boyle's. These are inversely related. Then we also conversed about Charles's law, which Charles's law is a relationship between volume and temperature. And that is, I'm going to go over here, V1 over T1 equals V2 over T2. This is Charles's. And this is a direct relationship. So essentially what that means is if volume increases, then the temperature will increase. Then after that, we had Gay-Lussac's law, which is a relationship between pressure and temperature. So you see that one depicted as P1 over T1 equals P2 over T2. This is Gay-Lussac's. This, judging by the relationship between volume and temperature, and then the equation for Charles's law, and then the relationship between pressure and temperature and the equation for the Gay-Lussac law, you can also deduce that this is a direct relationship, or these two properties, these two measurements are directly related to one another. Then last but not least, we have a relationship between volume and amount of a substance, written as V1 over N1 is equal to V2 over N2. And this is commonly known as Avogadro's law. And this is also a direct relationship. So I put boxes all around the ones that are direct relationships to one another. So Charles, Gay-Lussac, and Avogadro's are all directly related, or all those different entities are directly related to one another. Now, what is also being accounted for, what's kind of omitted here, is if you look at, say, Charles's law, there are a couple of things that are held constant. And this is true provided that the amount of the substance is held constant and the pressure. So we have variables that we're not going to change and keep those constant in order for this relationship to be true. So if I were to say something like, oh, the volume of a substance, you've increased the volume of a container that a gas is in, the temperature is going to decrease. Or it's going to, yeah, you increase the volume, the temperature is going to increase. but you also added more of that substance in. Well, then your relationship is not necessarily going to be true because if you're changing more variables, it's more difficult to, and it's less accurate to look at these equations. So we have to basically anything that's not listed is going to be held constant or it's expected to be held constant. So if we look at Boyle's law, what has to be constant? Well, we're comparing pressure and volume, so temperature and amount. Those two are held constant. Of these four different variables, temperature, amount, volume, and pressure, if whichever two are not listed in the equation, those are going to be held constant. So Avogadro's law, what's held constant for this to be true would be, well, volume and amount are listed. So pressure is not, so it's held constant. And then temperature is not listed. So it is also held constant. Gay-Lussac's, okay, pressure and temperature are listed. So what's held constant? That would be volume and amount. Now, of these variables and of these equations, knowing these um, four different measured quantities, we're going to get more into those a little bit when we or in the coming lecture because we're going to be talking about what's known as the or ideal gases and what is commonly known as the ideal gas law. Okay, so how do particles behave when a gas is heated? Well, provided that the amount is held constant and provided that the container that they're in does not change size or shape or anything like that, we can expect that when a substance is heated, the particles of that substance are going to move faster. I always kind of think about it like you know, if you are standing somewhere, if you're standing on, let's say that you're just standing outside on the hot concrete and it progressively gets hotter, are you going to stand absolutely still without moving? I mean, unless you're trying to like show that you're super tough and that, the soles of your feet are made of leather or something like that. No, you're going to move. You're going to be like, oh, this is really uncomfortable. I have to move. So the particles are like you and your feet. You're going to move faster. You're going to get away from that heat. You have more energy to do that. Now, here's all of our relationships. I think that it's important to go back and kind of think about these. I know that we just drew them out and wrote them all out, but let's go ahead and work through and see which ones there are. But let's talk about on the left-hand side, is it direct? Is it a direct relationship or is it an inverse relationship? And for this first one, we have an inverse relationship. For the next three, we have direct relationships. So what this means, and that's indicated right here in this column, if pressure goes up, then the volume will either go up or is it going to go down? Well, it's going to go down. If pressure goes up, then volume goes down. Next up, if temperature increases, then volume also increases. If temperature increases, pressure increases. If the amount of a substance increases, then the volume is going to increase. You're holding some things constant in all of this, though, and those are the items that we talked about on the previous slide. Now, I'm going to ask that you be able to identify these laws as well. If you do a Google search for mnemonics or something like that, gas relationships mnemonics, you're going to find some clever ones. I've always heard Boyle's law. It's called Boyle's law because you boil peas and vegetables. And it's pressure and volume, P and V. Um, in terms of a clever thing for the the other laws, I don't really know any other ones, just because I just kind of had to force them into my head. So Boyle's law, and then when we're talking about volume and temperature, this is Charles's law. The next relationship is going to be Gay-Lussac. And then our last relationship is Avogadro's. Now I'm using the terms relationship and laws kind of interchangeably. Um, and there's not really a rhyme or a reason. They are interchangeable terms. Some of them it's almost like the convention. Everyone knows this is Boyle's law, whereas others it might be more common to hear it referred to as a relationship. But there's not really a right or wrong. It's not like, no, this is absolutely the law. Now, what we have to get into though is, well, this is where all of these relationships, they're relationships between two different variables, pressure and volume, volume and temperature, pressure and temperature, volume and amount. Okay, so it's just two things. We're changing one and seeing the impact of the other. What if you change more than one variable, though? So, what if the temperature goes up and the amount of the gas goes down? Or what if the temperature goes up and the volume goes up? Like you can just try to imagine that you've got a gas in a Ziploc bag, and then what you do is you take the contents of that first Ziploc bag and put them into another larger Ziploc bag, all the while you're heating that system. It's possible to see both temperature and volume increase. But how does that impact temperature, or how does that impact pressure? How does that impact the amount of a substance? If you're changing more than one variable, is it possible to kind of have an expectation of what takes place? The answer is yes, there is. So these, all of these equations are relationships between two variables. We're changing one and seeing the impact on the other, while your other two variables are held constant. But that's not always what takes place. Instead, quite often we have more than one gas variable that changes. So what we have is what is known as the combined gas law. Now, the combined gas law is a law where we take pressure, volume, and temperature, and we set up an equation for our initial pressure, temperature, and volume, and we can equate that to a final pressure, temperature, and volume. One important variable is the temperature must be measured in kelvins. Now, if you remember from early on this semester, we talked about changes in temperature and adjustments for temperature. So 93 degrees Celsius, in order to convert that to kelvins, we have to add 273.15. And the convention is not to refer to this as, let's see, let's go ahead and add this up. 273.15 plus 93. Well, I'm going to say that's 0.15, 6, then nothing plus 7 is 16, so 1. So that'd be 366. So this is 366.15. One of the things that we talked about earlier this semester was this is 366.15 Kelvin, not 366.15 degrees Kelvin. This is 366.15 Kelvin. So the combined gas law, what you can do is you can say, all right, well, let's imagine that we have a T sub 1, D sub 1, T sub 1. So this is our initial state. So initially, we have a system where the pressure is 1.03 atmospheres. 1.03 atmospheres, and we've got a container that is 0.65 liters. So a little bit more than half of a liter. The temperature is, let's go with 290 Kelvin. Now, what I want to do is I want to calculate final pressure, volume, and temperatures. So what I'm going to do is I'm going to say that I have a gas sample that is contained within a bottle, and that bottle is 0.65 liters. The temperature is 290 Kelvin. Now, what happens if I take that same gas? So I'm going to say N is constant. The amount of gas that I'm thinking about with you when I'm using this combined gas law, I actually don't even care about it because it's going to be held constant. So I don't have to think about giving like assigning a number or amount to that. What I'm going to do is I'm going to say, well, the new temperature, I'm going to heat this sample up. My new temperature is that 366.15. We did that calculation, might as well use it. The volume of the new container that I transfer the gas into is 0.95 liters. Now, the question is, what happens or what have I seen happen? My volume goes up and my temperature goes up. Okay. Well, I could jog back a second and I can say, okay, well, what happens to the pressure when the volume goes up? Well, if I was just looking at these two variables, I'd be looking at Boyle's law, and I'd say if my volume goes up, then my pressure is going to go down. If my volume goes up, then my temperature will go up. Okay. So here, what I know or what I want to be able to do is I want to be able to calculate, well, what happens to my pressure if both volume and temperature goes up? So thinking about this, if my volume goes up, then I would expect if the only variable I was changing was my volume, if my volume goes up, then I would expect my pressure or my temperature, no, my pressure to go down. Okay. If my temperature goes up and that's the only variable that I'm changing, then I would expect my pressure to go down or go up. I'm sorry. So I have basically two variables that are kind of working in opposite directions with one another. So to solve this sort of equation, and to solve for, let me change that P sub 2. Sorry about that. My final pressure, what I'm going to do is I'm going to do some erasing first. And I'm going to set up my calculation right here. So P sub 1 is 1.03. V sub 1, 0.65. T sub 1, 290. That is all equal to P sub 2. I don't know that. I'm solving for it. V sub 2 is 0.95. T sub 2 is 366.15. Okay, so the way that I like to solve a question like this is I like to do 1.03, 1.03 times 0.65. To that, I get 0.6695. 0.6695. divided by 290. That is equal to P sub 2, 0.95, divided by 366.15. Okay, so 0.6695 divided by 290 is 0.0023086206, and so on. I've got this very long number. What I'm going to do with that is I'm going to multiply each side by 366.15. So whatever this number right here that I came up with, I'm multiplying it by, or sorry, this number is this one right here. I'm going to multiply that. I'm leaving it in my calculator. Let me go ahead and share my screen and show you that real quick. So it actually works like that. Perfect. So I got this in my calculator, but it's kind of an ugly number, so I don't really want to mess with it. So I'm going to multiply this by 366.15. That gets me a number that's a little bit more tangible. That gets me 0.84530, blah, 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 blah. Now this number, effectively, I've got 0.845, and so on. Let me draw a line to show where my work is equal to P2 times 0.95. So now I need to divide each side 0.95. Now I've left that 0.845 in my calculator, so it's not actually going to be 0.845 divided by 0.95. Instead, it's going to be 0.84530146551724114 divided by 0.95. And that's going to get me P2 equals 0.8. I'm going to round that to 0.89. 0.89. So P sub 2 equals 0.89. And then what are my units for pressure? Atmospheres. Okay. So the way that I like to think about this is we tweaked two variables. The magnitude of those tweaks impacts our end result, impacts what this P sub 2 is. If, let's say, the temperature, rather than going up to 366, went up to like 1,366, are we going to come out with the same number? No, we're not. In fact, in that case, the pressure would probably increase. We tweaked two variables. One was going to have a positive effect on the pressure, and the other was going to have a negative effect on the pressure. What ultimately happened to the pressure was it went down. Why is that? Well, it's because of the magnitude of those combined changes. So this is ultimately how you would work through a problem like this. And given the specific values, you're going to have a different number and different output. But again, if the volume went to, like if the volume shrank, you could still do this sort of calculation. It's important to look back and think about these changes and how they might impact the result, but then actually do the calculation and say, okay, how does this actually impact the result? So if we were to compare it and say, all right, well, both pressure and volume increase, what's going to happen to the temperature? Well, I would bet that if pressure and volume increase, then the temperature is probably going to increase, because if pressure individually increases, what did we see the temperature do? We saw the temperature go up. if um, volume increases, what did we see the temperature do? We saw that increase. So chances are that's what we would expect to see. In addition to that, when you see a division calculation, volume over temperature, these two things are directly related. Pressure and volume are over temperature. Well, then pressure, the factor there, the product that comes from pressure times volume is going to be inversely related with temperature. So this is another sort of calculation. A balloon filled with helium gas has a volume of 22.4 liters at 1 atmosphere and 0 degrees Celsius. Okay, when you take your exam on Monday and you see something like this, 0 degrees Celsius, I want you to break this down. I want you to say, hard stop, 0 degrees Celsius, that is not going to go in here. Instead, I'm going to take that temperature and I'm going to add to that 273.15. Okay. So what I want y'all to do is to see this question and effectively rewrite it. Say a balloon filled with helium gas has a volume of 22.4 liters at 1 atmosphere and 273 Kelvin. Just work to get to a point where you don't even recognize, I'm sorry, that temperature. Okay. Now, what is the volume of the balloon at 2 atmospheres and negative 50 degrees Celsius? Again, hard stop, negative 50 plus 273. Well, that's the same as 273 minus 50, so that would be 223.15 Kelvin. What is the volume of the balloon at 2 atmospheres and 50 degrees Celsius? Again, that's 273 plus 50, which is 323.15 Kelvin. So work to basically rewrite those questions right from the bat, from the jump. Now, with that in mind, one of the things that I think is important for you to recognize is this negative 50 degrees. That shows why we do not use the degrees Celsius scale. Why we use the Kelvin scale? Because the Kelvin scale is an absolute scale, meaning the lowest possible temperature is 0. There's no such thing as -5 Kelvin. The lowest that the coldest or the lowest temperature that something can possibly experience is 0 Kelvin. And when you start talking about 0 Kelvin, it's kind of like, it's not like, oh yeah, that's really chilly out. Instead, that is um it's still a theoretical 0. No one has ever observed something at 0 Kelvin, because when you get to that, it's kind of like you're bumping up against like the space-time continuum, and maybe that's where Doc Brown and Marty McFly have what temperature they had to get the DeLorean to. If you don't get those references, they're to a movie called Back to the Future about time travel. The point is that 0 Kelvin is like basically unattainable. Okay, so this question is using, let me erase my flashing out of T1 and T2. Essentially, this is saying, all right, well, what's the volume at 2 atmospheres and 223 Kelvin? Then what's the volume at that same temperature and that same pressure but a different temperature? So in order to calculate this, let's go ahead and knock it out. 273.15 Kelvin. 223.15 323.15 Kelvin. Okay, so effectively P1 is 1. V1 is 22.4. And T1 is 273.15. Okay, so then the A, I'm going to try to work these out in this condensed space here. If there's any part of this calculation that you don't follow how I went from step to step, just let me know. And I'm going to pull my calculator up, and then I'm going to share that as a part of my screen so that you can see the work that I'm doing. Okay, so I'll write all this out. P1 V1 equals P2 V2. I'm going to skip writing that out, and instead what I'm going to do is I'm going to write P1, which is 1, V1, there we go, there we go. V1 is 22.4 over 273.15 equals my new temperature, or my new pressure, which is 2 atmospheres. Okay. My new volume, which is unknown. My new temperature, which is 223.15. Okay, so what I've got is 1 times 22.4 is 22.4. So I've got 22.4. I'm just going to skip that multiplying by 1, divide by 273.15. Okay, so that gets me this 0.820062223, blah, blah, blah. Now I'm going to multiply this by 223.15. 223.15. That gives me 18.2. So now I'm going to divide this by 2, because effectively what I've got is, actually I'll write it out, 18.2996 equals 2 V2 divide by 2 divide by 2 divide by 2, and I get V2 equals 9.149 or 150, I'll call it 9.15. And that is the new volume. Okay, so effectively what that tells us is if we see the pressure increase and our temperature decrease, our volume decreases. Now let's see what happens when we've got P1, which is 1 times 22.4. So our initial volume and our initial pressure divided by 273.15 Kelvin equals our new pressure, which is 2 atmospheres, and our new volume, which is V2, divided by 323.15 Kelvin. Okay, so now we're going to do 1 times 22.4 divided by 273.15. Okay, so same number, times 323.15. Okay, now I've got 26.5 equals 2 times V2. So divide by 2, divide by 2, 13, or V2, 13.25. Okay, so let's think on this for just a minute. We see that whenever our temperature, so when our pressure goes up and our temperature drops 50 degrees Celsius, or drops 50 degrees, then we see the volume drop pretty tremendously from 22 liters down to 9.15. So cut by more than in half. Alternatively, when we see the temperature go up by the same magnitude, what do we see the volume do from its initial state? Well, we see it still get cut a little bit less than in half, but nearly in half. So what that tells you, or what I want you to take away from that, is to think about the magnitude of these changes. To think about, okay, well, how much would the temperature need to go up in order to offset that pressure doubling? So effectively, what would we have to do in order for that volume to stay at 22.4 liters? Well, your temperature would have to go up by more than another 50 degrees, probably more than 100 degrees. So when you're doing a combined gas law calculation, have a sense of the impact that each variable has, but then be careful when you're answering it and excuse me, what your ultimate outcome of that question is. Okay. So then question is, what if you know all of the gas variables except for one of them? We have what is known as the ideal gas law. The ideal gas law is PV, pressure times volume, is equal to N, the amount, the number of moles, times R times T. This is sometimes commonly referred to as Hübnert, and I don't know if that's helpful at all, but some people like to do that. PV equals nRT. I always thought that it was just easier for me personally to remember PV equals nRT. Is that a really creative mnemonic or anything like that that helps me out? No, not at all. Instead, it's just PV equals nRT, which is just, I think that shows maybe the lack of creativity I sometimes have, but nevertheless, I never really thought of it as like an indictment of me as a person. This equation is one that you can use to understand how a ideal gas behaves. So you can make a calculation about the amount of gas that's in a container, provided that you have P, the pressure, the volume, this R value, which spoiler alert, I will give this to you, and the temperature. So basically what I could do is I could say, hey, there's this Ziploc bag. This Ziploc bag has nothing but carbon dioxide in it. The volume is, you know, zero point 0.3 liters. The pressure is 0.97 atmospheres. And this is at, you know, 296 Kelvin. You would be able to figure out the number of moles or the amount of CO2 that's in there based on that information. Because effectively, working with the ideal gas equation or the ideal gas law, which is shown here, all that you need to do is just rearrange components. So make it PV over, you want to figure out or solve for N. So you're saying PV over RT equals N. So we can do this sort of calculation shown in A. What volume is occupied? Okay, so stop right there. What volume? V is our volume. So what we want to do is rearrange this. We're going to divide each side by P. P will cancel because it's in the numerator and the denominator. Then we've got, I'm sorry, just one moment. So Pressure will cancel out on the left-hand side, and we'll be left with this equation that is V equals N R T over P for pressure. Okay. Now, what we want to do then, let's say, all right, well, we can proceed through the rest of the calculation. Occupied by 0.5 moles. Okay, so that's going to be our N value. So I'll write N right here. And one thing that's important to know about this is occupied by 0.5 moles of a gas. It doesn't identify the gas. It doesn't say that it's hydrogen gas or carbon dioxide or carbon monoxide or methane or ethane or methanol or ethanol or any gas. It doesn't say that because it doesn't matter. The identity of the specific gas does not matter. Now, R, that R value, I will provide that to you on your exam. So you've got that. So I always like to, kind of check things off. So V equals question mark. N, check. R, check. T, ooh, 25 degrees Celsius. So that's going to be 298.15 Kelvin. And then pressure, 1 atmosphere. 1 atmosphere. T is 298.15 Kelvin. So check, check. So now it's just, again, let's pull the calculator up. You could just Alt tab over and get it that way. Share, full screen. So I'm going to say my N value, which is, I always like to do, let's see, is my calculator? There we go. 0.5 times R 0.0821. If you look up R, if you Google R value, you're going to find a couple of different ones. So I would recommend always kind of deflecting to this one. 0.5 times 0.0821 times T, which is 298.15. That gives us 12.239 divided by my pressure, which is 1. What volume will that gas occupy? 12.24 liters. Okay, now we can do the same thing down here. Moles of a gas, that's our N. 10-liter container, that's V, 25 degrees Celsius or 298 Kelvin. That is our temperature. So now what I've got is PV equals nRT. Let's see, I've got my temperature, I've got my R, I've got my N, and I've got a volume. What I don't have is pressure. So basically move anything that has a check by it to the same side. So move each side, the volume. And now I've got T equals nRT over volume. So now what we're going to do is do that calculation. What is my N value? 0.5. What is my R value? 0.0821. What is my temperature? 298.15. I've solved for the numerator, which is 12.23. Is that funny that that's the same number that we came up with previously? I mean, like funny haha, not particularly. Funny like a coincidence, yeah. I wouldn't read anything into it. It's not like, aha, I've cracked the code. It's always, come up with 12.23 and then divide by the square root of 7. No. Okay, so 12.2390575 divided by my volume, which is 10, and I get pressure equals 1.223. So that's the way to solve this sort of ideal gas question. PV equals nRT. Now, the ideal gas law, you are going to use this when the amount or when you are given the amount of a gas, or when you're asked about the amount of a gas. Now, pressure for this, let's look at this. Let's look at our ideal gas constant. This tells us our volume is in liters, because I'm looking at this, or the units right here. Liters, then this dot means times. So liters times ATM divided by K times mole. Okay, so K is temperature, mole is amount, ATM is pressure, and L is going to be volume. Okay, so the ideal gas law, we're going to use that when we're given the amount of a gas. The pressure must be used in atmospheres. So if you had something that was like the pressure was provided in another unit, then you'd have to have kind of a fresh start and say, okay, well, how do I convert that? And it's entirely possible that would be given in the equation, but, or given in the question. Um, but your pressure must be in atmospheres. And the ideal gas law, PV equals nRT. I will not give you that equation. I have the expectation that you learn that equation. Now, the combined gas law, okay, this was where we were changing the conditions. We were changing the environment. If we jog back here, we use the combined gas law because we saw our balloon that was filled with helium gas, which it has a volume of 22.4 liters, and the pressure was 1 atmosphere. What happens when the volume, or what's the volume when the pressure goes to 2 atmospheres and the temperature goes to this? We change two variables. Now, I think it's always kind of a clue that you're given a prompt that says your initial amount is this, your final amount is this, then you're going to be setting things equal to one another. So your combined gas law is where you're changing the conditions. Now, PV or P1V1 over T1 equals P2V2 over T2. I'm not going to give you that equation either. I'm not going to give you really any of these equations. I do expect you to know them and be able to know them to identify them, as well as to use them and to know the relationships that they describe and the nature of those relationships. Okay. Both of these laws, they are going to have a temperature that is measured in Kelvin. So again, I will give you that conversion. Your degrees Celsius plus 273.15 equals your temperature Kelvin. So both laws, and basically any of these laws, we have to know the temperature measured in Kelvin. So add 273.15. Now, this is a nice summary of all of those laws. Boyle's law, Charles's law, Gay-Lussac's, Avogadro's, the combined gas law, and the ideal gas law. Like I said, I will give you the R value, that gas constant, but the equations, I need you to solve those, or I need you to know those. Now, one thing that is common amongst Boyle's, Charles, Gay-Lussac's, and Avogadro's law, well, and the combined gas law, is you can rearrange these all. I gotta erase that. You can rearrange all of these equations and set them equal to K. K is just kind of a placeholder for constant. Um, And it's basically just a measure of the ratio of these two things to one another. So Charles's law, you could think about that as a good ratio calculator for the volume to the temperature. Gay-Lussac's is pressure to temperature. Avogadro's is volume to amount, and Boyle's law is a it's not a ratio, but the product of pressure times volume. So this is a nice summary slide. What I would do if I were you is I would make sure that I feel good about these right here. And I'm going to just kind of scribble these out because it's just sharing that as kind of insight that these are ratios. Make sure you know these and the names associated with them for your quiz today as well as your exam on Monday. Now, your exam on Monday will be like all of your other exams. It will start at, or the window to take it will start at 9:30. Um, if you have any questions between now and that exam, please don't hesitate to email me. Um, in terms of how can I practice, I think that it's very helpful to just come up with equations or come up with calculations and say, okay, well, try to think about it, try to find things in your day-to-day life that list volumes and say, okay, well, if I go to grab um, let's say a 20-ounce bottle of Dr. Pepper. 20-ounce bottle of Dr. Pepper is approximately, um, I think it's like 567 or something like that, or 467. No, it's more than half. Um, a Dr. Pepper bottle is 567 milliliters. Well, 567 milliliters is 0.567 liters. Okay. What would happen if I put a gas in there and I heated it up? But I also applied pressure to it and I heated it. What's going to happen to the volume of that? Just trying to plug numbers in and set them equal to one another. This is also helpful because you can do a calculation where you plug values in here, here, and here, solving for everything over here on this side, the right-hand side of the equation. And then you can flip it and reverse it. And what I mean by that is say, okay, well, my final state is my initial state. Can I solve for how I started the problem? If the answer is yes, then you're manipulating that equation properly. If no, then you probably need to look back at your work. Um, if you do a Google search for combined gas law calculation questions, you're going to find some good ones. I'll post a couple just sort of practice worksheets if I can find keys with them. But combined gas law, the ideal gas law, and all of our gas relationships, those are going to be, I would say, close to half of your exam on Monday, maybe a little bit more than half. So when you think about that, say, all right, well, each of these components will, or sorry, each one of these relationships has a person kind of associated with them right here. So I want to be able to, or I will ask you, what is Boyle's law? What is the equation for Charles's law? What is Avogadro's law? Be ready to solve those sorts of, or answer those sorts of questions. I'm going to stop my recording.